Welcome to Daily Papers, the podcast where we break down the latest fascinating research into bite-sized chunks.
Today, we're prying open one of the biggest black boxes in modern technology, the artificial intelligence behind language models like ChatGPT. These models are called transformers, and while they're incredibly powerful, how they actually work is often a huge mystery, even to the people who build them.
Exactly. It's a bit like having a magic box that can write poems and code, but you have absolutely no idea what's going on inside. And sometimes that magic box makes weird mistakes, gets things wrong, or just completely makes stuff up. This is what researchers call hallucination.
A new paper proposes a way to build these AI models differently, not as mysterious black boxes, but as transparent white boxes. The project is called PRISM, and it's based on a really elegant idea. What if the AI's main job is just to separate a signal from noise?
Okay, signal from noise. Let's break that down. What does that mean in the context of language?
Think about reading a story. The signal is the important stuff, the plot, the characters, the cause and effect relationships. It's understanding that a character who finds a key might later use it to open a door. That's the deep, long-range meaning.
And the noise?
The noise is the less critical, local stuff. Things like grammar, syntax, or the statistical fact that the letter Q is almost always followed by a U. It's important for making sentences that make sense, but it's not the same as understanding the story's logic. The problem with current AIs is that they often mix these two things up.
So PRISM is designed to neatly separate them. It's a transformer, but built from the ground up with a new set of rules. The researchers introduced two big ideas to make this happen. The first one is basically about giving the AI more mental workspace.
Right. They call it an overcomplete dictionary. A simple way to think about it is this. Instead of having one messy notebook where you scribble down plot ideas and grammar rules all on the same page, you give the AI two separate, clean notebooks. One is labeled Signal, big ideas and plot, and the other is Noise, grammar and local details.
By giving the signal and the noise their own dedicated space, they don't have to compete and get jumbled together. That makes sense. But what's the second idea? Because this is where it gets really clever.
The second idea is about how to keep the information in those two notebooks from ever interfering with each other. The researchers treated the signal and the noise as waves with different frequencies.
Like radio stations?
Exactly like radio stations. The signal, the long-range plot connections, is represented by a low-frequency wave, like a deep bass note that can travel a long way. The noise, the local grammar, is represented by a high-frequency wave, like a short, sharp cymbal crash.
So you have a low-frequency signal channel and a high-frequency noise channel. But radio stations can still sometimes get static if their frequencies are too close, right? How do they stop that from happening?
This is the coolest part. They made sure the ratio between the signal frequency and the noise frequency was an irrational number. Specifically, they used the number pi.
Pi? Like 3.14159, the number from high school math class?
That's the one. Because pi is irrational, it goes on forever without a repeating pattern. It guarantees that the signal wave and the noise wave will never perfectly align. They will never resonate or create interference. It's like tuning your two radio stations to channels that are mathematically guaranteed to never, ever overlap. They call this technique pi rope or pi rope.
That is genuinely brilliant. So does it actually work? How did they test it?
They trained their small PRISM model on a dataset called Tiny Stories, which is exactly what it sounds like, a huge collection of very simple children's stories. It's the perfect controlled environment to see if the AI can learn to separate plot from grammar.
And what did they find?
They found that the model did it all on its own. Without being told to, the different parts of the AI's brain, called attention heads, started to specialize. The low-frequency signal heads got really good at tracking long-range meaning.
For example,
in a sentence like, "The frog found a shiny key. He looked for a door," the signal heads would light up, making a direct connection between the word key and the word door, even though they were far apart in the text. They understood the logical link.
And what about the noise heads?
The high-frequency noise heads focused on local grammar. They'd pay attention to the relationship between the words for and in the phrase for a door. They were handling the syntax, leaving the other parts of the AI free to think about the plot.
So, by designing the architecture with these clear physical principles, the separate notebooks, and the pi-tuned radio frequencies, the AI just naturally organized itself in a way that makes sense.
Precisely. And this has huge implications. It suggests that performance and interpretability aren't a trade-off. We don't have to choose between a powerful AI and an understandable one. We can have both. It's a shift away from the brute force method of just making models bigger and hoping for the best, and a move towards more elegant, intelligent design. It's about building an AI based on first principles. The PRISM model shows that by thinking of language as a simple combination of signal and noise, and by using some clever math to keep them apart, you can create an AI that is not only effective, but also one whose decision-making process we can actually follow. It's a big step towards building AI we can truly understand.